I appreciate, again, being here to talk to you guys. I'm pretty passionate about compressors, strange as that sounds. And I've been doing a lot of work on maintaining elevated gas temperatures through the compression process. It has a lot of benefits. The main benefit we're going to talk about today is reducing tank vapors because that's a hot topic. So I will mention some of the other benefits because Larry referred to them. We're going to start out with some physics, right? Everybody wants to start out with physics. Gas gets hot when it's compressed. It's called the adiabatic heat of compression, and I'm hoping this will start the animation. Okay. So when we compress gas, the molecules don't like getting crammed together, and they get hot. And when we compress it, right here at the end of the cycle is when we let it out through a discharge check valve, and we let hot gas out of that compressor. Now, we have to cool the gas in order to continue compressing it. Normally, when you compress gas, when you get up to about 300 degrees, any temperatures above that, you risk your lube oil failing on you, and you can have the piston and gall in the cylinder. So we stop compressing the gas when it gets hot. And so to achieve the pressures we need for gas lift, we might have to have typically 3 compression stages. And what happens, though, when we cool the gas after each stage, we're overcooling it. And that is causing us some problems. We're creating problems for ourselves by not taking care of, by allowing it to get cooler than it should get. So the next thing I want to talk about from the mechanical engineering thermodynamics is the phase diagram. And if this thing has a pointer, oh, no, I guess not, backwards. All right. Well, I wish I had, is there a pointer on this, Bruce? I apologize, I guess not. All right, if you look at the far right-hand side of the curve, the yellow vapor region, there is a pointer right here, sorry. This scale is temperature, minus 200 to about plus 150. And this scale on the left is pressure, 200 to 1400. If your gas is in the yellow zone, that's called the vapor region. It's 100% vapor, no liquid. And that line is the hydrocarbon dew point line. So if you allow the temperatures to fall from 100 down into the 50 range, you're going to be in the two-phase region. That's the blue area. You'll have a mixture of liquid and vapor. If you continue letting it fall in the gray region, it will be 100% liquid. And typically, you've got to be minus 100 for that. And that's what happens in the cryogenic gas plants. They cool your produced gas down to below 100, and they knock out all the liquids except for methane, put the methane in the pipeline, and make products out of the other stuff. So we need to see what temperatures we need with our gas to stay in the yellow region where we only have vapors present. Because when we condense hydrocarbons in the coolers, those liquids go into the next stage of compression. Now, to protect that compressor from seeing those liquids and damaging the compressor itself, we have a scrubber on the inlet of each stage of compression. We'll remove the liquids and send only a vapor to the next cylinder. So what happens with these liquids that we collect in the scrubber? They go to your tanks, typically. And so they're in those tanks. Remember, these were a vapor when they went in the compressor. They got pressurized and cooled, and they became a liquid, and they go back to an atmospheric tank, which is a much lower pressure than what the gas was when it came to your compressor. They tend to vaporize and create problems for you. So we want to see if our gas, we want to know what the vapor diagram, what the phase diagram looks like for your gas. And we have an easy way of doing that. Anyone here familiar with the Ariel Compressor Company? I see a couple hands. Yeah, that's a very common industry-accepted compressor. All the rental companies have them. A lot of operators own them. And they have a very easy-to-use design program that's free. and they have paid the Virtual Materials Group out of Houston to put in some hydrocarbon, some process simulation program in it that will tell us how much of this liquid is going to condense. So just pulling from the website, the Virtual Materials Group provides its clients with proven, validated, and robust thermophysical property prediction packages for the hydrocarbon and petrochemical industry, and they're backed up by extensive data and development support. So we can run this program and we can create the phase diagram. And that's what I did using, the first example is for a gas well in my backyard of East Texas, a Cotton Valley gas well, and it's lean 0.65 gravity. And you see the shape of the teardrop here, and the hydrocarbon dew point curve is right here. And I ran it on a 30-degree day. And what that gave me was how, if you're not familiar with compressors, when we cool the gas, we typically design cooling tubes that will take the gas coming out of that hot cylinder and cool it within 30 degrees of ambient temperature. So if it's 30 degrees outside, the gas is going to come out of that cooler at 60. If it's 100 degrees outside, it's going to come out at 130. And the exception for that is the final cooler, the third cooler. That's designed bigger to really cool the gas down to 15 or 20 degrees of ambient. So on the third stage, if it's 100 degrees outside, you'll have 115. Why? Because when we have a gas well, we want to wring all the water out of it, because we're sending it to a dehy, taking the rest of the water dry so we can put it in a pipeline and send it up to the East Coast to heat homes. We don't want any hydrate issues. So all these compressors that we have up here doing gas lift work were designed to sell gas. And they had really big final coolers on them to get get that gas as cool as possible so the dehydrators would work. All right, so back to this diagram here. You see a stair-step kind of a stitching here. That's the path that the gas takes through the compressor. In this case, it starts at 80 degrees, the bottom scale, and about 60 pounds, and it gets compressed to 200 pounds and 220 degrees. That's what the program predicts. Then it goes through its cooler back down to 60 degrees. Again, the 60 degrees is the 30-degree approach and the 30-degree ambient temperature. It's inside the two-phase region, so we theoretically should have some of this gas being turned into a liquid if it wasn't lean. And then the next step, we compress it to 400 pounds in the next stage, cool it again, compress it in the third stage to 1,000, cool it again. So that's the phase diagram for this. But since the gas is lean, we don't have any hydrocarbons falling out. And this is an output of the program. And this was a pretty healthy sized compressor, 4993 MCF per day. And it says the only thing that was being condensed was water. We lost 25 MCF a day of water vapor in the first cooler, 4 MCF a day in the second cooler, 2 MCF a day in the final cooler. But we didn't lose any hydrocarbon because the gas was lean. So what if we repeat this exercise with Bakken gas? This is an actual run that I got from JW Power, one of their compressors. They had loaded the gas analysis in it that they got from the operator. And the green curve is actually further out. The one I showed before, you might note that the green curve was about, the farthest it ever got was about 120 degrees. This one, the farthest out the green curve gets is about 145 degrees. So the premise here, I thought, okay, if I put in the program that I'm not going to cool the gas below 145 degrees, I should not have any hydrocarbon condensation because I'm in the 100% vapor region. The blue line is this is the water dew point curve. So looks like I'll have a little water form in the second cooler and the third cooler, but not in the first. So let's see what the program said. And this is another program output. This particular compressor said it would move 888 MCF a day. I've highlighted some of where these values are. And in stage 2, it would have 6 MCF a day condensing. That's that value right there, 0.006 million. And it would be 99.4% water. In the third stage cooler, you'd have 2 MCF condensing, and it's 99.91% water. But no hydrocarbons were condensing. So this is what we want. If you're putting 888 MCF a day in there, you want all 880 other than water going in your well. So let's say, what happens if operator comes by and he opens all the louvers up because he doesn't know that we're intentionally trying to stay at 145 degrees, and now the cooler is dropping all these temperatures. Instead of the right-hand side of the line, they're on the left-hand side in the 2-phase region. What would that do? I mean, 75 degrees is pretty easy to do. Like this morning, it was 31 degrees. With a 30-degree ambient approach, we'd be at 61, cooler than this example. But then this afternoon, it might hit 70 out here, it'd be 100 degrees. It's pretty easy for things to get neglected and louvers to not be closed when they need to. So let's see what the run said in that case. This is actual compressor with Bakken gas in it. It says now we're going to have 16 MCF a day condense in the first cooler. That 16 MCF a day is 0.3 something GPM, which is 13 barrels a day. So 16 MCF a day is going to condense into 13 barrels a day and go to your tanks. That's 1.6% of the inlet gas going in that compressor. Stage 2, it's the same story, only worse. We're going to condense 53 MCF a day, turns into 36 barrels of liquid, which is 5.6% of your inlet stream. Total of 49 barrels a day is dumping to your tanks from those 2 scrubbers. Now, I haven't mentioned about the third stage cooler. There's even more condensation in it, but it's not going to the tanks. And the topic of today's discussion was reducing tank vapors. But if you're running a gas lift operation, you don't want the liquids condensing in the third stage cooler. There's typically no scrubber on the discharge side of the compressor. You just run it to your wells. So you don't want that liquid going into your well and being handled by your gas lift valves. Also, if it gets cool, those liquids will form hydrates once the temperature falls down to about 70 degrees. So you're going to have to inject methanol and things like that. You're probably going to end up in this case having more than 10% of your inlet stream condensing into hydrocarbons. Earlier I mentioned that if we went in the phase diagram, if we stayed to the far left-hand side, that's what gas plants did, cryogenic gas plants. Take it to minus 100, take out all the liquids. Think of these compressors as really poorly performing gas plants. They're stripping your liquid out. You don't want them to do it. You want it to pump it all downhole. But because we're not watching the temperatures, it's condensing a bunch of liquids. So, next page. All right, I wanted to show you what the program said these liquids were going to consist of. It's not just propane, or it's the whole mix. Coming out of the first stage coolers going into the second stage scrubber, you've got methane, ethane, and propane. It's about 30%. And the rest of it is gasoline type of components, butanes, pentanes, and then some diesel-y components. Got the whole mix there. The scrubber the third stage inlet scrubber, which is handling the gas coming out of the second stage, even more methane, ethane, and propane. That's about a little over 60%. So when those things get dumped to a stock tank, they want to vaporize. And will they, considering we created 49 barrels a day out of 69 MCF, will you have 69 MCF vaporized in your tank? You could have more, you could have less. It could take some of your crude oil with it. Or it all depends upon the temperature of the crude in your tank. But anyway, that's just to let you know it's what the gas that's, what the hydrocarbon consists of and why you have the tank vapors that you're seeing. That's because it's got a bunch of methane, ethane, and propane in it. Okay, so it's our choice now to control the cooler outlet temperatures. We have to decide, are we going to control them or not? Maintaining cooler outlet temperatures above the hydrocarbon dew point will prevent condensation of your rich hydrocarbons because you're not sending them to the tanks anymore. You don't have any to send to your tanks. And your tank vaporization will not be elevated because they're not present. And if you had some, I think here in North Dakota, the regulatory body said don't dump compressor scrubbers into your crude oil tanks because it's raising your vapor pressure. Dump them to like a water tank. You may not even have a good way to get rid of them. You may have to haul them off to disposal, these liquids. I don't really know what you do with them if you can't put them in your crude tanks. So anyway, of course, if you maintain cooler outlet temperatures above the hydrocarbon dew point, there's other benefits, such as warm gas injected into well is good for your corrosion chemical program. Corrosion chemicals love 150 to 200 degree range. You won't have any hydrate problems because they form at 70 if you're in the 150 degree range going to your well. And you don't need to inject any methanol, so you're going to save some money on methanol pumps. If you don't control the cooler outlet temperatures, if you just get a run-of-the-mill compressor and you put it out there, you're going to have hydrocarbon condensation in the wintertime unless you're taking methane on that tailgate of a cryogenic plant. You got a pipeline quality gas. And there's not a lot of that going on. Okay, here's a picture of a little one-well gas lift compressor, 75 horsepower. And I put it up there to say, how are gas outlet temperatures normally controlled? Because some of you aren't familiar with this. And here is a handle controlling the louver section. There's not an individual handle for the 3 stages, just one handle for all stages. And there's not an actuator on it to do anything automatic. That's pretty typical, even on larger compressor packages. Now, how do we keep temperatures elevated? Well, there are various automated temperature control systems. I remember first hearing about how Canada used to recycle the hot air coming out of the top back to the inlet of the cooler using, ductwork. JW Power, who's a platinum sponsor here, they're the only compressor company that's affiliated with us that I know of. They are working with my little company to offer several temperature control options. And what we're going to on future ones, typically people use pneumatic actuators that are controlled by Kimray T12s. They're difficult to operate. But what we're going to in the future is I guess I can't get my video to play there. Yeah. Sorry about that. Had a nice video. That thing there it goes. It's shutting now. There's actuators for everything. We don't need to use old technology of a pneumatic actuator that vents to atmosphere. We can do it all electrically now. And so I guess that's about it. There's a lot of other benefits to keeping warm temperatures, and I think maybe if we might have a question about that, I'll follow up. But Bruce, that's the end of my presentation officially.
Okay, well, thank you. Are you going to keep me up? The Commission's oil conditioning regulations do require. Maybe it was on me. Sorry about that. The Commission's oil conditioning regulations do require that you keep a vapor pressure of 13.7 or less, and we do prohibit the liquids to be re-injected back or put back into the tank. So according to your first phase diagram, it appeared that if you were staying at above 120 degrees that you wouldn't be sending those butanes back to the tanks. Did I get that right?
Yes, that's exactly right. Go back to that slide. It's a simple premise. The vapor region, if your gas is to the right of the dew point curve, all the molecules will exist in the vapor phase. And in this case, it was 120 degrees. It was about as far as you had to go. With this was just an example that was well illustrated, so I showed it up. But your Bakken gas, it's about 145 degrees.
So you started talking about some of the benefits of the warm gas being injected downhole. Why don't you tell us a little bit more about some of the other advantages of that?
Okay, I think I have oops, got to go back down. I have a slide on that for extra in case. Okay. If we were able to keep the temperatures in the 100% vapor range on the far right of the curve all the way to the wellhead, well, your compressor is going to like that. A lot of times these liquids condense in the cooler. They can form hydrates in the cooler and plug the cooler off. Your gas can't get out of the compressor anymore, shuts down a high discharge pressure. Gets cold in the next 6 hours while a man comes out to start it when it's minus 20 out. It's really, you don't want it. So that's the hot temperatures minimize hydrate formation, not only in your cooler, but in your flow line out discharging from the compressor, in your sales meter run, and in your choke body where you may be using multiple chokes to prorate the gas amongst multiple wells. If you got that warm gas, you don't have to worry about hydrates forming in them. Typically, everybody injects methanol. I mentioned earlier, warm corrosion chemicals work better if you talk to your chemical company. Ask them if that's a true statement. Now, one thing I like, if you've ever been around, I've been around and started a lot of compressors. And when you're running compressors with rich gas, and it's the gas is condensing in the cooler, and it comes out of the cooler at the bottom, and it runs along your skid, and then the piping turns up and goes in the interstage scrubber. You get that liquid collect in that pipe that's laying horizontal on your skid. A little bit, maybe 1/4 inch, maybe a 1/2 inch. Until it comes time to restart your compressor, and the guy has 10 other compressors to start, and he goes over to the blowdown valve, and he goes, whoosh, and he rips that machine, and a very high rate of gas blows through it and cleans all those lines out, and it sends that condensate that was in the bottom of those lines out through your vent pipe. And you, as I mentioned earlier about lube oil being rated 350 degrees, lube oil collects with that hydrocarbon condensate. So it's not just pure distillate that's going to evaporate in the air. You've also got it combined with lubricating oil, which doesn't go away. It makes a mess. And you will find most operators know not to park downwind of the compressors when they're going to blow them down. So I like that it doesn't make a mess. Now, if you've got 10% of your compressor throughput vaporizing, you need a 10% bigger compressor to get the gas you want out of it. So that's another advantage. You get more out of your compressors. You're paying for a certain rate, but you're not getting it. And when you put more gas in your well, your performance is better. And it's well known in the gas lift circles that if you have paraffin issues, you won't anymore by putting warm gas in it. Warm gas is a good cure for paraffin issues downhole. And in the Eagle Ford, we actually did some testing with that by elevating the temperatures. We had a problem on every gas lift well with building paraffin on the upper 1,500 foot of pipe, and that's when I was working with EOG. And as soon as we elevated the temperatures to 150, injecting down the annulus in this case, we had no more paraffin issues. So it's good all the way around.
Well, thank you very much.